we want to create a flux in the air gap that is, so we want an air gap flux density that is given by Bg is equal to B0 plus B1 sine omega E t, where B0 is equal to 0.5 Tesla and B1 is equal to 0.25 Tesla. So we have a DC and an AC field, and we'd be applying some particular frequency. And we are told that we have two different types of magnet material, and I'll show that in a minute. So we have a Hitachi NMF 34B a ferrite magnet material, or the other option is NMF 12F Hitachi ferrite magnet. So the question is, which one should we use? So we have two questions we want to answer. Find the magnet length Lm and the magnet area Am that gives the desired DC air gap flux density and minimizes the magnet volume. So we want the smallest magnet volume. Okay, so that's A. And then we and then B is we want to work out what current excitation. So this is fixed, right? So this must be due to the magnet, but this is variable, so this must be due to the current. What current gives us 0.25 Tesla variation in the air gap. So we want to figure that out, and we need to make sure that we can look at that on the BH curve. And the important thing would be to check if the material was not a hard magnetic material. You have to make sure you don't demagnetize it. Particularly if it's hard magnetic material, you'd be a bit better off. So B is find the max value of the current of the current I that gives desired B1 value. Okay, that's the problem. Now we're given a couple of other things here. We're going to assume that the air gap area is equal to 5 centimeters squared. The air gap length is equal to 0.4 centimeters, and we have 250 turns. Okay, those three things are also being, we're told. Right. Okay, so how do we do this? So the first thing we'll do is we'll find A, and so we need to get this 0.5 Tesla. So this is actually not too tricky. I'm gonna erase this. You have the questions. So now, so let's just write out a few things. So we have HM LM plus HG LG is equal to NI. Okay, and we also have BM AM is equal to BG AG. So I'm saying that the flux flows all the way around and there isn't any leakage with this assumption. So I'll call that 1 and this is 2. And we also know that, and we'll assume we've got a hard magnetic material, and then we'll talk about that more in a minute on the BH curve. So we're going to say that it's a hard magnetic material, and so it can be modeled using this equation here that we've used before. Okay, and we also know that BG is equal to mu naught HG in the air gap. Now, so what we're going to do is we're going to look at when I is 0. So we're going to do it in two parts. So we have we can model this as two MMFs, and we'll look at each one separately. So we've got the NI, and then we've got the HC LM. And this is RML, and this is RG. That's the magnet reluctance, and this is the air gap reluctance. So if I is 0, then we're just looking at this case here, and here in equation 1 we've got HM. HM is related by 3 to BM and BR, right? So there's quite a lot going on inside of this HM. So but let's set what I equal to 0, and then so I'm just going back and deriving the equation that I did before just briefly. So so we can write H. So we can look at equation 2 and 4 and get rid of the BG in there. So let's write this. So let's write 4 as HG is equal to BG over mu naught, and then looking at equation 2, we have a BG, so we could substitute for BG, and then we have BM AM divided by mu naught AG. I just put equation 2 into here. So that's 5. Okay. So now we've got this in terms of Hg. So we can now eliminate Hg from equation 1 and write equation 1 only in terms of magnet material. So and we've made this 0. I equals 0. We're looking at the first case. So 5 into 1 gives HM LM plus BM AM LG divided by mu naught AG. And so rearranging, we have BM is equal to minus HM mu naught AG LM divided by AM LG, like that. Okay, or we could write this as BM divided by mu naught HM is equal to minus HG AM times LM LG. So we had that relationship before. Okay, so now we can, now this over here, what is that equal to on the left? Remember, BM is equal to mu naught mu r HM. So this part on the left here is equal to mu r is equal to mu r. So we can that's a property of the particular magnet material we are using. So we can get that off of the BH curve. Okay, let me pull that up. Okay, so now this is a BH curve for the NMF 12F. It's written there. That's a ferrite magnet material. Now there's a whole bunch of different curves on here. Now you can see first of all we've got these different magnetization curves. That's showing the magnetization plot for the magnet material, and you can see that if you get this is within the magnet material, this is the M versus H that we talked about in the previous lecture, and then you can see these lines along here. These are the BM versus HM lines that we also talked about in the last lecture. So we talked about in the last lecture how you could model the M and H and the B and H. But in this lecture we just talked about the B and H. So we don't want to get to the point where we demagnetize the magnet. And you can see that, so this top one is for minus 60 degrees. So they have different temperatures. And so you can see that for the example where we have minus 60, we have a relatively high BR. But then coming down here, if you get below about 0.15 Tesla, then you're going to start to demagnetize the magnet. So what we'll do is we are going to use the 20 degrees Celsius BH plot, and so that gives a nice straight line almost. We'll approximate it to be a straight line. And then we have a BR of 0.46 Tesla and an HC of 350 kiloamps per meter down here. Okay. And then these parabolic curves are the related to the energy product lines, and we talked about that a little bit last time. So last lecture. So and then we also have the other magnet material, which is shown here. This one is the weaker one. This is the NMF 3B. This one, again, if we look at the 20 degrees, it has a BR maximum of 0.4 Tesla, and then coming along down, now you can see this is 20 degrees. You can see that it, if we get below 0.15 Tesla, it will start to demagnetize, which is a problem. So we're going to model that as a straight line, and then you can check to see that we don't go below this 0.15 here. This is an approximation, making this straight line. So, but we're going to do that for this this class discussion. Okay, so we'll take that to be a straight line. And then, so when you assume it's a straight line, and it's pretty much certainly a straight line for this 0.461, then the maximum energy point is actually halfway. So that would be half. So it would be 0.23. Okay, so looking at these BH curves then allows us to determine the relative permeabilities that we need for the linear region. Okay, so I'll write down the relevant information that we need as we go now on the board. So for the so what we'll look at first is the NMF 3B with the when we have this being the BR and this is the HC, it's a triangle, and then in this case this is an approximate. What I'm going to say is approximation of it's not a pure triangle, but we're going to use this to give it a reasonably good point. So the point where we will maximize the energy is the middle. So to maximize the energy, then we should have that the BM is halfway, and so that I took off the BH curve to be 0.204. So this is BR over 2. Okay, and then so in that at that point, at that BR, at that BM, this is the BM here. We can then get the HM. So this was around 300. Right? Let me just double check that. Yeah, 300. And so so we have HM as 0.24. Yep, 0.204, and then HM is equal to the 150 times 10 to the 3 amps per meter. Okay, so with the BM and the HM from the BH curve, we can get out the well, we can get out quite a lot, but we'll get out the relative permeability for sure. So let's put that in here. So we got 0.204 divided by mu naught 150 times 10 to the 3, and so that gives us 1.082 for the mu. Okay, Now remember what we're trying to get? We want to get 0.5 Tesla in this air gap. And we also know what the area is. We know what the area is. So, and then we also know now what the BM should be to maximize the energy usage of the magnet material. If we're maximizing it, we're operating the magnet at its maximum energy point, that would mean that we will minimize its volume. Okay, so that's important. So, we want to operate at BM equals 0.204 to minimize the volume. To minimize volume. So we need BG is equal to 0.5 Tesla in the air gap. So then the only thing we don't really know is the area of the magnet, because we know that flux G is equal to flux M. So we have BG AG is equal to BM AM. We're told what BG is. We're told what AG is. We know what BM should be to maximize the energy. So then we can figure out AM. So AM is equal to BG AG divided by BM. So this part's really quite straightforward. So it's 0.5 times 5 centimeters squared divided by 0.204, and so that gives us 12.255 centimeters squared. Now you may ask, well, why don't we choose BM to be 0.4, the top, because then we get a smaller area. Yeah, okay, but think about where you'd be operating on the BH curve, right? This is our BH curve here. We can't operate at this point because we have a load line. We have this load line. It's going to determine where we are on the BH curve, and that load line is dependent on the material lengths, the material properties, and the lengths and the areas as we've derived. So we can't choose to be up here. We can choose some of these regions down here, and that will govern the gradient of the load line that we get, and we can select our geometry to be at that, have that particular load line gradient. Okay, so if it turns out that if we get it right in the middle, we'll have the smallest magnet. So we've got the 12. We've got the area being 12 centimeters squared. Okay, and then now we can find out the length. So now we can use the other. So the equations that we derived before, which was equation 6, I think. Equation 6, yeah. So equation 6, we can. So we had. Let me rewrite it. We have AG divided by AM LM divided by LG. That's equation 6. So now we want to find LM. We know everything else in here, so we can figure it out. So rearranging, we get LM is equal to minus BM We get Lm is equal to, so I'll rearrange, minus Bm mu naught Hm, and then we've got Lg Am over Ag, like that. Okay, the minus goes away because the Hm will be in the negative direction across here. It's negative value. It's a negative number, and so that will give us a positive Lm. So we have so we can plug in the values. So we have so this. So this is the relative permeability, but if we put an Hm in that's negative, it will give a positive out here. So we end up with 1.082. That's the relative permeability term, times the Lg. Lg is 0.4 centimeters. So that's 0.004. And then we have Am over Ag. So we found Am, that was 12.254, and the Ag is 5. So that gives us 0.0106 meters, or 1.06 centimeters for the length. So that's the length of the magnet. Okay. And so the volume then is the multiplication of the area and the length, and that gives the volume for the volume of the magnet. This is for the 3B is equal to 12.99 centimeters cubed. Okay, so we can do the same thing for the other grade of magnet material. And so for the, I'll just run over that briefly. So for the NMF 12F, we want to be at 20 degrees. The BM should be selected to be 0.23. That's BR divided by 2. Then that will get, then we can get the mu r. So that's, we can just take that from one point. So if we choose the 0.23, the corresponding HM is 174,000, and so then that gives 1.052. That's the relative permeability. So the relative permeability is close to 1, but it's not 1. Okay, and then now we can get the area. The area is BG AG divided by BM. Now because we have a larger BR, the BM is higher, and so we get out 0.5 times 5 centimeters squared divided by 0.23, which gives 10.869 centimeters squared. Okay, and then using the same LM equation, we can substitute in, and we get out 1.052 times the Lg, which is 0.004, times 10.869 10.869 divided by 5, and so now that gives 0.91 centimeters. So it's a bit less, but because that length is smaller, then the total volume for the 12F grade ferromagnet is 9.89 centimeters cubed. And compare that to the 3 grade, which was 12.99. So the question, if is it worth it? Well, it will depend on the material cost of the 12 grade versus the 3B grade, so that would be one of the considerations, and then another consideration would be looking at its demagnetization characteristics. Okay, so that gives us the dimensions for the magnet, and so now the second question is, what current should we use to give this 0.25 Tesla variation? Okay, so that's the last bit. Right. So now let me erase this. So now the B, what current excitation is needed to give the plus or minus 0.25 Tesla max. So we can go to the equation we derived earlier when we have the two, when we both have the MMF sources, equivalent sources. So we've got the current source and the magnet source, and we found that the magnet material is flux density would be equal to Lm divided by Am Rg times Hm minus Ni Lm times Rg divided by Rg plus Ml, where the Ml, remember, is the length of the magnet divided by mu naught mu r Am, and the Rg is equal to the Lg mu naught Ag. Okay, so we know what these two are. We can put in the numbers. So we have Lg is 4 times 10 to the minus. No, let me do the top one first. The magnet reluctance is equal to the length of the magnet. So I'll do it for I'll do it for the 3 grade. So for the NMF 3B, I'm doing it for that. So for that one, we had the Lm being 0.0106, and the area of the magnet being 1.2255 times 10 to the minus 3 meters. Okay, so with those numbers, let me just write it out again. So Lm is 0.0106 divided by mu naught, and then the mu r was 1.061, and then we have the Am, which I just said, 1.2255 times 10 to the minus 3, and that will then give us 6.487 times 10 to the 6 amp turns per Weber. Okay, and then the other term is Rg. That is the Lg divided by mu naught Ag. So that is 4 times 10 to the minus 3. And then we've got the mu naught, which is 4 pi times 10 to the minus 7, times the area of the gap, which is 5 times 10 to the minus 4. And so putting that all together gives 6.366 times 10 to the 6 amp turns per Weber. Okay, so we want the Bg to be 0.25 when we just, due to the current excitation. So we want the Bg to be I didn't do that bit. Did I? Here it is. Okay, sorry. All right, so we want the Bg to be, we want Bg to be equal to Bm Am over Ag, right? Equation 8. So if we look at this here, the first part here is the DC part, and the second part here has got the current excitation in it. So we could write that out. So we can rearrange so what I'm going to do is I'm going to rearrange this so that it's in terms of the air gap flux density, because this is in terms of the magnet material. So we've got Bg equals Bm Am Ag. So if we substitute the Bm and the Bm we've derived here into this one, we'll get it in terms of Bg. So this is equation 7. This one's 7. So we'll put 7 into 8. 7 into 8, and then we get out Bg is equal to, so the AMs cancel, and then we have minus Lm Ag Rg times Hm minus Ni Lm Rg divided by Rg plus Rml, like that. Or we can note that so we can expand these two out. Let me write another line here. So we have Bg is equal to minus Lm Ag Rg Hm plus, and now the Rg's cancel and the Lm's cancel, and so we get out plus Ni divided by Ag 1 over Rg plus Rml sine omega E t. Okay, like that. Now this sign, so now we've got this negative here, but that's just that's just the polarity direction of this and the polarity direction of the current excitation, right? So we could, we can switch these two around by the, the definitions of what is plus and minus. So let's just do that. So we want this to be plus or minus, and this one to be plus. And so then, because this can be either, right? The current can be either, depending on the polarity. So then what we got was you might not like what I just did there. Okay, let me write it this way. So this can be plus or minus, right? Because we could change the polarity. Well, this is sine. So the first term, let me write it this way instead. This first term here has to equal 0.5, and so we got that. So because we had HM oh, I think I'm missing a oh. Okay, that's fine. So this first term here can be written, we determined previously. So this term here is the equal to the 0.5 Tesla. We got that in the first part. So then we can write that we have the 0.5 Tesla for the DC part, and then we need this part to be the second part to be determined, and so we have the Ni Ag 1 over Rg plus Rml sine omega Et, like that. Okay, so that part, this part here needs to be 0.25, and so we can figure out what the current is. So the current, so we need, therefore we need to get Ni divided by Ag 1 over Rg plus Rml to equal 0.25. So we can rearrange this and we get out I is equal to 0.25 times the area of the air gap times Rg plus Rml divided by the number of turns. And so putting in the numbers, so therefore I is equal to area 250. what's the area of the, oh, no, that's it. Okay, is equal to 0.25 times 5 times 1 times 10 to the minus 4. That's the, gosh, getting tired. This is 5 times 10 to the minus 4. That's the area of the air gap. And then we got to times that by the two reluctance terms. So we have 6.366 times 10 to the 6 plus 6.487 times 10 to the 6. And then we divide that all by 250 and we get out 6.42 amps. So that will then give us the current. Now you can then substitute this back in to the, I'm not going to do this here, but we can substitute this back in to the BM equation to look at where we're up. This is the, so when we're applying this current, when the current is opposing the flux, we will be moving out further down the BH curve. This is the BR, this is the HC. And then if we're applying the current to add to the flux of the magnet, we'll be moving up the BH curve. And this variation will be determined by the current excitation, and this gives the maximum to get that 0.25 Tesla. Okay. Now let's just repeat for the other grade of magnet. So I'm going to erase this. So for the NMF 12F grade, we have that we can do the same analysis. So the current is going to be again equal to the we can write the flux in the gap times the reluctance in the gap times the reluctance in the magnet divided by the number of turns. And so the RG and the RML are the same. The RG is the same. The flux is the same because it's, here, let me write this. So the RG is the same, which is the 6.366 times 10 to the 6. That doesn't change. Amp turns per Weber. The flux doesn't change because we're still wanting the same 0.25 Tesla. So that's the flux times the area. So that's 1.25 times 10 to the minus 4 Webers. That doesn't change. The thing that does change though is the magnet reluctance. That's going to be lower because the length is lower. So we have Lm divided by mu naught mu r am, and so that term was 6.33 6333243.7 amp turns per Weber. So with those three things, we can then obtain the current, which is substituting in so substituting in those where the N is 250, I get out 3.18 amps. So that's that's a significant reduction in the current required to get that 0.25 Tesla, and that's due to the magnet, mainly due to the magnet length, and the area as well. So they're different. Okay, so I will stop there. Thank you.